The presentation is by Mr. Andrew Booth, Global Business Manager, Panduit Cable Cleats, a Fellow of the Institute of Engineering and Technology and a senior member of IEEE. Mr. Andrew holds a master's degree in Leadership of Innovation from York University in the UK. He has almost 25 years of experience in the design, testing, and manufacturing of cable cleats. He has vast experience in international business leadership and direction, has been involved in the preparation and maintenance of the international standard IEC 61914 cable cleats for electrical installations since its inception and is currently the nominated US expert. A very warm welcome and over to you, sir, for your presentation.
Good afternoon, good evening, everyone. My name is Andy Booth. You've kindly already introduced me. I'm a chartered engineer, a fellow of the IET, and a senior member of IEEE. So we start with a very simple definition of what a cable cleat actually is. And I take the definition from the IEC standard 61914. A cable cleat is simply a device designed to secure cables when installed at intervals along the cables. So the standard at this point doesn't bring into question materials or physical size. So you can see here the examples across the middle of the screen are from Panduit. So they range from the flexible strap product, a strong stainless steel cleat, an aluminium cleat, or a heavy duty strap product. But the examples given in the standard are along the bottom, and you can see the variety of materials, designs, and physical sizes. So why are cable cleats necessary? In a three-phase system, we have three sine waves, all very equal, 60 degree, same height, same depth, and they're all very symmetrical. In the event of a two-phase or a three-phase fault, two or three phases join together, and we get this asymmetric curve, the fault curve. The important thing to note here is that very first peak, noted IP. So that is the peak of the short circuit in kiloamps. You can see after that first peak, we drop, dip below axis, and then rise back up to the axis. That is one cycle. So on a 50 Hertz system, we get 50 cycles. 60 Hertz, we get 60 cycles. So you can see where that one cycle, and then a bit further along, the 3 cycles, then the 5 cycles, those are cycles or Hertz within that time frame. The highest forces, why are cable cleats necessary? The highest forces occur at the first quarter cycle. So that very highest peak on the first curve, that is the peak of the short circuit. And on a 50 Hertz system, that occurs in 5 milliseconds. So that's when those electromechanical forces between conductors are at their highest and most destructive. And we'll see the importance of that in a moment. On the subject of circuit breakers, quite often a very quick circuit breaker will interrupt a fault at 3 cycles. So the circuit breaker has to recognize the fault. It's then got to do its mechanical part or electrical part to extinguish or drop the fault. A very quick breaker will stop at 3 cycles. The highest forces occur at a quarter of a cycle. So just bear that in mind when we start talking about the cables and the speed. So do short circuits happen in cables? They happen every day out in the field. Generally, it's a breakdown of a cable insulation. Sometimes that can be electrical or thermal, but in the majority of cases, the breakdown of insulation will be mechanical, and whether that's through human error or whether that's just through poor installation. You see the images at the bottom of the screen. The one on the far left is a direct dig through, so that was a buried cable, and the equipment went straight into the live conductor. The next one was an XLPE cable, where actually on examination there was a wood screw found in the insulation, which eventually caused the short circuit. The middle example is taken from a rail installation in the UK. So the guys were lifting live cables, and what they were doing was changing some cleats. And the guy who was moving the cable thought he'd put the cable up on that piece of strut, which you can just see at the bottom of the image, he'd actually placed the cable on that threaded studding. So the studding became live, the strut became live, and the person who unfortunately was injured, electrocuted, was some 3 meters away. He touched a live structure 3 meters away from this, but it was all to do with that puncture of the insulation. The next image, where you can see the cables are worn away, is actually taken from an oil and gas platform in the North Sea, where the cables went from one platform over to another, floating platforms. And obviously those platforms move in relation to each other, and the cables were just laid and looped. And eventually, a matter of weeks actually, the insulation just wore through, and a short circuit brought both rigs, the main rig and the support rig, to standstill for 48 hours. And then things like joints, terminations, general equipment failure within the cable installation can lead to a short circuit. So what actually happens during a short circuit? You can see here we've got 3 single phase cables laid in trefoil. This is a standard IEC testing rig. You can see the 5 cleats in the center of the picture there are our tested cleats. We need at least 5 to comply to the standard. The big heavy clamp on the right-hand side, and there's also one on the left-hand side just out of the image, is an over-engineered end condition clamp, and that takes all of the movement and cable split and effects of the cable out of the equation. So we're testing 5 true trefoil cleats on the rig. Just bear in mind, before we show the video, the ladder, the cable ladder, which we fasten to, is 600 millimeters wide. So that's a 600 wide ladder. And quite often out in the field, we don't just have one layer of ladder, we have numerous. We have stacked ladders with very little space in between, maybe 200-300 millimeters. Certainly in projects like data centers, we can see up to 10 rows of ladder above each other. So just bear that in mind. This is a product produced by Panduit, but we aimed far too high on one of our initial tests. So we run the high-speed video at 10,000 frames per second, but as we saw in the graph, this all happens within milliseconds. Now, all of this movement is purely down to the proximity of those conductors. They are touching in trefoil. The fault force turning basically into electromagnetic force. So those cables there, 500 millimeters squared copper conductor, class 2 copper conductor, very difficult to bend by hand. And you can see the damage caused purely by magnetic forces. So obviously the cleat on this was underspecified for the level, the short circuit level. But you can see the cables have actually spread by 600 millimeters. They've only been stopped by the side walls of the ladder. And anything above this ladder would also be taken out because of that top conductor. You can see the amount of force has pulled in the end conditions of the ladder. And you can imagine this is only a rig of maybe 3 meters long. If you've got a 50 or 100 meter run, the damage has been limited here by the length of the rig. You wouldn't have that on site. The damage would be much higher. So this here is a multi-core cable. So this is, it's an unarmored multi-core cable, but we get the same effect with a steel wire armored or aluminium wire armored cable, albeit to a lesser effect, but we still see the same effect on an armored cable. This is an unarmored cable. Again, at the right-hand end, we've got connection to generation. Left-hand end just out of short copper buzz bar to induce the short circuit. This was a 3-con 95 tested to the installation level given. When we carried out the short circuit test, this is the effect of a short circuit on a multi-core cable. So there's a perception that the jacket of the cable, and even more when you've got the armor in the jacket, will protect the conductors in the event of a fault. This is untrue. The jacket serves no protection at all. It's there purely to keep the conductors together, to make it as one cable. The armor, when the armor is included, the armor is there to stop forces from the external, so dig-throughs. The cables within that multi-core still act exactly the same as 3 separate cores. The physics are the same, the electromagnetic forces are the same. This is the effect of a short circuit within a multi-core cable. So we'll mention our calculator, the way we specify a cleat later in the presentation. Even when we consider multi-core, we consider a cable cleat. So what should happen? Again, this is a Panduit product. You can see we've got more than 5 tested cleats. You can see the end condition cleats carry out a short circuit. Now there's the peak, but then because the cleats are holding those cables, we get the AC effect. So we get the on-off effect of those magnetic forces. What we've got to do to meet the IEC requirements, we've got to carry out that first short circuit test, and we've got to hold that decaying RMS fault for 100 milliseconds. So as well as the initial forces at peak, we let that RMS diminish until it almost gets to a steady state, but we've got to hang on to that RMS for 100 milliseconds. To meet a category 1, to meet a class 1 test, we are allowed no loose or missing parts, and we cannot damage the cable. We cannot damage the jacket to the cable. Any damage to the cable, any loose or missing parts, we fail. If it's all good, if it's a successful test, the cleats are still there, no damage to cable, we do not tighten anything up, we don't adjust anything, we go back to the control room, hit it again with a second short circuit of the same level, and again, no loose or missing parts, no damage to cable. If we pass that, we take the rig away from the connection, we spray each cleat for 2 minutes with water, we then apply a voltage withstand check for 2 minutes. So we'll put through it 1 kV, all 3 phases to earth, 1 kV AC or 2.8 kV DC for 2 minutes. If we hold that voltage, then we can assume that there is no damage to the jacket where we can't see it within the cleat, and we get a category 2 test. So every single Panduit cleat has a category 1 level or a category 1 success at a certain peak level, and then we've got a full category 2 level at a slightly lower. But for all of our range, we've got very high levels at class 1 or category 1 or category 2. So many national standards like the wiring regulations here in the UK or the NEC regulations in the US, they have a very top level statement, something like you should install your cables to protect against electromagnetic forces. And that's all it will say. It won't tell you how. So that's why we developed the IEC standard. We don't just look at forces during a short circuit. We look at many other different characteristics of that cable cleat. So we rate our cable cleat for temperature, -60 up to +120, carry out various tests at that low or high temperature. We check for resistance to flame propagation. So if there is a fire, will this cleat contribute to the spread of flame? It's very similar to UL 94, where we basically hold a flame against the cleat, allow any polymer to drop onto a piece of paper, and we check, for self-extinguishing properties and that sort of thing. Lateral load testing, which is the bottom right image. Essentially, it's a tensile loop, a bursting strength of that loop around the mandrels or cables. We look at an axial load resistance, the top right image. So we need to know what sort of force we can withstand of cables in a vertical application, such as in a wind turbine or through 90 degrees on a standard installation. How much or how many newtons, kilonewtons, can that cleat withstand? We look at impact resistance at low temperatures. So if we declare the cleat at -40, we have to take the cleat to -40, take it from the freezer, clamp it within 10 seconds, and drop a known weight from a known height upon the cleat. And we check for fractures and we check for damage. We carry out full corrosion resistance and UV resistance. If the cleat is an all steel cleat or all metallic cleat, we don't check for UV, only a polymer cleat. If the cleat is made from stainless steel, for example, with more than 16% chromium, we don't need to carry out the corrosion test. But for things like galvanized steel, hot dipped or post galvanized, we carry out full salt spray resistance to corrosion. And then we carry out the resistance to electromechanical. Now that bottom one, we've got to use an accredited laboratory. So the lab has to be accredited to an IEC 17025. So it is capable of carrying out tests to another IEC standard. All of the other tests above Panduit have their own in-house equipment, and we're UL regulated, and we've got full engineering capacity to carry out all of our own tests, except that bottom one where we use an accredited laboratory. What we have also developed, and we're the only company in the world that have their own software to do this. There are many different types of simulation software. Last year we won, or the year before, sorry, 2019, we won best in class for our development of a standard piece of software. So a standard piece of simulation software will look at the mechanical properties of a material, and it will show you any torsion moments, it will show you the stress, strain, but it doesn't take into effect the soft jacket of the cable, the flexibility of the cable cleat, the structure that the cleat is fastened to, and all the materials within the cleat. So what we've developed is a piece of multi-physics simulation software where we put in not just a generic cable, we will model in your cable. So the right conductor, the right amount of strands, the right amount of material, the right jacket with the right shore hardness. We then put our cleat in with all of its known properties. We then fasten it to your structure to suit your installation, and we can simulate 2 short circuit events. So we don't just look at the mechanical properties, we look at those magnetic field vectors, the Ferencian forces, and we put everything together, and we can examine not just the failure of the cleat, but will it damage the cable, the direction of those forces, etc. So we simulate it, we get a good product on the simulation software, we then build up a rig identical, and we will take it to that independent test lab for validation. And we have scores and scores, probably hundreds now, of validations. And where do we use cable cleats? Well, wherever you have a power cable with a fault potential, doesn't matter what vertical, any of these verticals, you have power cable, you also need cable cleats for that power cable. I think that's it. Thank you very much for your attention.